It's your boy, Math Times Cool. Was that a good introduction? That probably seemed a lot cooler in my head than it actually was. Probably. Okay, let's begin. Thank you for tuning in. Okay, let's go, fam. What mistake did Jack make in his definition of a rotation? So pause the video, do it, and then come back. Let's go. For the center point C, the image C is at the same point as C. Okay, calm. For any point that is not at C, rotation of theta about point C creates P1, such that CP is equal to CP, and that PCP is equal to theta. Yes. The answer is A, because the one key detail that Jack forgot was the direction. Yeah, clockwise or counterclockwise. Let's go. What transformation does the mapping define? Every point A on line L maps on line M maps itself. Every point P that isn't on L maps such that point P is parallel, or such that line L is the perpendicular bisector of PP. Okay, that was yes. So let me just draw this out real quick. Okay, so you have line. So every point P. Wait a second. Oops. Every point P. Let's name this P and name this point A. So A would map onto itself, and then P. Okay, this is not exact, so don't worry. This would be a new P. This line L would have to be even though this doesn't look like a perpendicular bisector, this should be a perpendicular bisector. Yeah, my drawing should have been like right there. Wait a minute. Yeah. So let me just, okay, this is really bad. Delete, fam. Delete. Okay. So, whoops. Yikes. So this, stop. This, you have P, A, and A maps onto itself. And then P1 is here. This should be perpendicular to line L. So P to P, the new P, should be perpendicular. Perpendicular and should bisect the length. So let's go. Point A maps to point A. Calm. Every point P maps to point P such that PP is parallel to AA and points in the same direction, which does not fully define a translation. Oh, which counterclaim, sorry. So, no, that's calm. It would be this one. Yeah, because this person says that they have to be facing in the same direction, so this would not work. This is a translation, and it also matches his description, but he doesn't say that they have to be the same length. So yeah. Layla tries to define a rotation. What mistakes did Layla make in her definition of a rotation? For the center P, the image C1 is the same point as C. Okay, calm. For a point P that is not C, a counterclockwise rotation of theta about point C creates point P1 such that PCP is equal to theta. Okay. Rotation. Yeah. Yes, okay. Because PCP must be perpendicular to CP. That's not necessarily true. Yeah. Because that should be the angle of rotation, which does not have to be 90 degrees. It needs to include the distance between. It depends on the angle. Yeah, so it doesn't need to include a distance, because it would be like this. Whoops. Yeah, this would be the P and the P1. Yeah, it would be an angle. Yeah. Okay. Did not make it. She did not make a mistake. Well, she did. Yep. Okay. Let's go 100%. So I think this episode, I'll just make it like, or this video, I'll make it like 20 minutes. Yeah, I just feel like they're a bit too short. So, which of the following must be preserved under the sequences of transformations? That would be both, because they are all rigid. A dilation, a rotation, horizontal stretch. Which of these are preserved under the sequence of transformations? Neither, because a horizontal stretch is, if you can map onto a shape onto another shape using horizontal stretch, they are neither congruent or similar. Let's go. Translation, dilation. Which of these must be preserved? Angle, because a dilation is not rigid. A rigid transformation. Okay, a reflection, rotation, and translation. That would be both. They're all rigid. Okay. Please, could you guys tell me if my videos are kind of boring, because I don't know, they might be, but I'm trying to make them fun. Let's go. So this new shape is a result of translating this shape 5 to the left and 5 down. So which of the following properties have been unchanged? So seems to have the same angle, yes, because they have been translated and so rigid. All of these would be, all these would have been preserved because they used only rigid transformation, dilation. So select all of the correct statements about the unchanged properties of ABCD, quadrilateral, and the ABCD, and the new shape. Sorry. Okay, so this new shape is the result of rotating by 60 degrees. BC and BC are both parallel to the y-axis. That is not correct. That is not calm. B and B are the same angle. That's calm. D and D have the same coordinate. That is not calm. Because D is not the center of the rotation. So this new circle, the new circle, is a result of reflecting the old circle across the line out. Select all of the answers that apply. Yes, radii, same circumference and area, because rigid transformation. Okay, so this new triangle is a result of this triangle translated by 6 units to the right and 2 units down. Okay, so angle A and A, same measures. B and B, same coordinates, no, because it's translated, and the areas, same. Very calm. Let's go, fam. Okay, we just completed. Did I just say let's go, fam? Okay, so this next I can. Feel free to read it. Yes. Okay, so yes. So let's quickly do this. Let's go. Come on, let's go. Let's go. Let's go. Oh, let's go. Oh, let's go. Oh. Okay, which of the following symmetries apply to these isosceles trapezoids below? Symmetrical if you reflect over y equals negative x. Let's see. Let's see. See. This seems 2, 3. Okay. Wait. No, it's not calm. 4. Wait a minute. X. Oh, okay. It is calm. Okay. So to see if they're symmetric, so the new point would have to be perpendicular to this. So it would be x. So if you can map onto the other shape, if you were to draw that a function for slope of 1, so it goes up, it changes by 1/1. And then just on any of the points, see, it increases by 1. Good. And then we can check it here. Actually, yes, it is. Okay, yeah. See, look. See, it increases by 1. And if we were to do it from any point, it should match. So yes, a 90-degree rotation about symmetry, or about point -1, 1. No, because if you were to just rotate this by 90 degrees, this point would end up like somewhere around there. Okay. Reflection symmetry over the line y equals -7x. So it'd have to be 1/7. So here, 1, and then 7 across. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And that doesn't work out. It would have to be right there. And so not symmetric. Hey, let's go. I think we'll only do 2 because these are kind of long. Okay, it has reached the 11-minute mark. So make sure to get yourself a glass of water. So I have a bottle of Gatorade right here. So this would be like ASMR. I don't know. Is that very appealing? Okay. Sorry for if that made you kind of uncomfortable. I don't know. I kind of needed water, and you should go get some water, and then be ready for the next part. Let's go. Pause the video, and get yourself a nice warm glass of water, or cold, I guess. Unless you're getting milk, that should be warm. Okay, let's go. How many lines of symmetry does this circle below have? Infinite, or ultimate lines. Because no matter where your line of reflection is, it should always be able to reflect onto itself. So, what is the magnitude for rotational symmetry? Well, this is pretty simple. It's, of course, all of them. All of these examples, because a circle, it would be a set of points that are equidistant away, so no matter where your line of reflection is, it should always map onto itself. Excuse me. And with the circle, if you just had the radius, and then you were to rotate it by any number of degrees, let's say you rotate it by 360 degrees, it should map onto itself. Sorry about that. There was a bit of commotion in the background, but don't worry. We can continue with class. Let's go. Let's get it. Okay, what was that? Okay, I'm actually sorry that time. Okay, let's do this real quick. Okay, so it's been reflected over line y equals 3 minus x. And so, like I said before, since the slope is -1, you take the perpendicular of that, which is 1, and then so you can just count. So you can see that it goes 1, 2, 1, 2. So here, and then this would be the same for this point. So 1, 2. Whoops, 1, 2, 3. 1, 2, 3. Calm. This should be it. Okay. Oh shoot. What kind of shape? This is a trapezoid. Trapezoid. Because as you can see, one set of parallel lines. Yep. Okay, let's go. Wow, okay. Great job. We've gotten a decent amount of stuff done in today's class. So, rotation symmetry, the amount of times you can rotate it, rotate a shape, or the amount of times you can map a shape onto itself, rotating it by a maximum of 360 degrees. So, for example, this shape, you can rotate this by 180 degrees and 360 degrees, and so the line of reflection is only 2. And then the line of reflection, the amount of lines it has that you can reflect over a part. So let's say you had this part, and you reflected it over this line, you would get this shape, and then this part, and then that part, and vice versa. And then for polygon, the line of reflection, is equal to the number of sides, and the rotation symmetry is the number of sides of the regular polygon. So yeah. Okay, let's go. So develop definitions of rotation, reflection, and translation in terms of angles, circles, perpendicular lines, parallel lines, and line segments. Okay, here. Yikes. Okay. So while it's loading, make sure to check out my calculus playlist. I'll probably make that. I'll probably record it today, and I might upload it tomorrow. And I was also thinking of maybe uploading a series where I just do like random math puzzles. I don't know, like stuff like. I saw this cool YouTube videos like proving 1 + 1 is equal to 3 or something. I mean, stuff that's like very entertaining. Okay, let's go. What single transformation has been applied to this quadrilateral to get this one? That would be dilation, because you can obviously see that it has gotten bigger. Okay. Translation. Oh, okay. What single transformation has been applied to A to get B? Looks like a translation, because not a rotation, not a reflection, not a dilation. It hasn't changed shape. It looks like it's been moved to the left and then down. And what has been applied to A to get B? This seems like a rotation. Yeah, because if it was reflected, it would be something like this. Yeah, it would have to be. Oops. It would have to be facing this direction. Yeah, it can't be upside down. Then translation, it would be facing this direction, because you'd just be moving it. And then dilation, it would change the shape. Okay, what has been applied to this shape seems like a rotation. Yep, not a translation, because it would if you were to just translate it, the points wouldn't match up. Reflection, again, if you were to reflect it over any line, these points wouldn't match up. And then dilation, they have not changed shape. Let's go. Okay. Okay, this is probably the last one. What mistake did Anju make in her definition of a reflection? For any points R on the line of reflection, the image R is the same point as R. Okay. For any point not on the line of reflection, the image is on the other side of L, such that PP is perpendicular to L. Okay. Okay, so this is what she forgot to include. Yeah, she forgot to include that they must be the same distance away from the said line of reflection. They can't just be, quote unquote, on the other side. Okay, what translation does this mapping define? Point P maps to point the new A, or A maps to the point the new A. Every point P maps to point P such that PP is the same length as A, and PP is parallel to AA and is pointing in the same direction. That should be simple. Translation. Okay, which counterclaim shows that Luke's definition does not define a rotation? For the center of P, the image C is the same point as C. Okay, the distance between each pre-image and image are equal. Okay, for any point that is not at C, a counterclockwise rotation of theta about point C creates PP such that CP is equal to new CP and PCP is equal to theta, which counterclaim shows that Luca's definition does not define a rotation. I read this, or do this. Okay, let's see. See. The police are after me. Just kidding. Okay, let's see. So counterclockwise rotation of theta about point C, creating P1 such that CP is congruent to new CP, and that P is equal to theta. Okay, so I believe that would be let's see. Okay, this is kind of a tricky one. I think. Oh my gosh, the disrespect, fam. I got this question wrong. Okay, this is not a rotation, and it doesn't match Luca's definition. So, it's okay. I didn't see that he said CP has to be congruent to CP. In that case, this is not a counterclaim. Oh, yikes. Yeah, it'll be this, because this is a rotation and also matches his definition, so it's not a counterclaim. But he did not fully define it. Okay. I am fully ashamed of myself. Oh shoot. This is the first mistake. Yikes, okay. For any point R on the line of reflection, the image R is the same point as R. For any point not on the line of reflection, L, the image P1 is on the other side of L, such that P and P are the same distance from L. What mistake? Okay. So, let's see. PP must be perpendicular to the line of reflection. Yes, it would be this, because whatever the distance is between P and L, there are infinite many points on the other side, and so that are the same distance from L, and so the PP must be perpendicular to line L. Let's go. So we are wrapping off. Develop definition of rotations, reflections, etc. So this is what we will be doing tomorrow. Okay. Thank you for staying tuned, and make sure to watch the previous episodes to have a better understanding of high school geometry as a whole. So my videos are here to educate. Thank you for watching. Just thank you for watching and putting up with my weirdness. Okay. Goodbye, and thank you.